Our goal is to understand and derive f sub yx at the point a comma b. Let z equal f of x comma y. F sub y means the rate of change of the function z with respect to y. Important: f sub y does not mean the rate of change of y. F sub yx means first find f sub y, and then differentiate that result with respect to x. So the order is first y, and then x. Choose the first point P1, equal to a comma b. Choose the second point P2, equal to a plus h comma b. The y-coordinate of both base points is the same, namely b. The change in x is a plus h minus a, which is h. Therefore, these two base points differ only in the x direction. Next, we measure f sub y at each of these two base points. At P1, equal to a comma b, keep x equal to a fixed. Now move y from b to b plus k. The old function value is f of a comma b. The new function value is f of a comma b plus k. Therefore, the change in the function is f of a comma b plus k minus f of a comma b. Divide that change in the function by the change in y, which is k. Now let k tend to 0. This gives f sub y at a comma b. Let us call this first function rate value, r1, equal to f sub y at a comma b. At P2, equal to a plus h comma b, keep x equal to a plus h fixed. Again, move y from b to b plus k. Here, the old function value is f of a plus h comma b. The new function value is f of a plus h comma b plus k. The change in the function is f of a plus h comma b plus k minus f of a plus h comma b. Again, divide the change in the function by the change in y, which is k. Let k tend to 0. This gives f sub y at a plus h comma b. Call this second function rate value r2, equal to f sub y at a plus h comma b. r1 and r2 are not rates of y. They are two values of the rate of change of the function z with respect to y. The same function rate is measured at two different x positions. So the change in that function rate is f sub y at a plus h comma b minus f sub y at a comma b. The corresponding change in x is h. Therefore, the average rate of change of f sub y with respect to x is the following: f sub y at a plus h comma b minus f sub y at a comma b divided by h. Now let h tend to 0. This limit is f sub yx at a comma b. Notice that the complete calculation uses 4 nearby points. They are a comma b plus k, a plus h comma b, and a plus h comma b plus k. Now substitute both f sub y formulas into the formula for f sub yx. We obtain the limit as h tends to 0 of the limit as k tends to 0. The numerator is f at a plus h comma b plus k minus f at a plus h comma b minus f at a comma b plus k plus f at a comma b. The denominator is h times k. First, k tends to 0. This finds the rate of change of the function with respect to y. Then, h tends to 0. This finds how that function rate changes with x. Let us check the idea using f of x, y equal to x times y squared. First, differentiate with respect to y. We get f sub y of x, y equal to 2xy. At the first point, f sub y at a b is 2ab. At the second point, f sub y at a plus h, b is 2 times a plus h times b. The change in the function rate is 2 times a plus h times b, minus 2ab, which simplifies to 2hb. Divide by the change in x, which is h. 2hb divided by h is 2b. Let h tend to 0. Therefore, f sub yx at a b is 2b. This agrees with direct differentiation. The derivative with respect to x of 2xy is 2y. Memory step 1. First y. Take a tiny vertical step k at each base point. Memory step 2. Next x. Compare those function rate values across the horizontal step h. Remember, 2 base points in x and 2 small measurements in y. Most important, we compare rates of the function z. We are never calculating a rate of y. Final meaning. F sub yx tells us how the rate of change of the function with respect to y changes as x changes.